So once again, we're going to say good evening to everybody. I'm Joe Deli Carpini, the Science and Operations Officer, and with me tonight is one of our top-notch meteorologists, Rodney Chai, who's a frequent contributor to our webinars. So we're going to take you through a review of this January 16th snow event. Not a big one across the area. It was mostly rain for everybody, but did produce some heavy snow in the higher terrain. And these are the more challenging events for us as forecasters. So we'll show you a little bit kind of what we went through in the forecast process. So with that, I'm going to let Rodney start us off with a presentation on the January 16th elevation snow event. Rodney, go ahead and take it away.
Yeah, thank you, Joe. Those of you who live in Western Massachusetts may remember this event, especially if you live in higher elevation, above 1,500 to 2,000 feet. That was a pretty impactful snow event for you guys. But for the rest of us, away from the high terrain, it was mostly a rain event. But let's take a look at this high terrain event. So this is a snow map depicting the observed snow totals. And as you can see, it's really concentrated along the spine of the Berkshires. And in particular, the higher you go, the more snow you get. And places like Rowe and East Hawley, you're talking about around 2,000 feet. And further north into Vermont, which is outside of our forecast area, they actually got over 16 inches in some locations. So pretty impressive, if not localized event. And with the heavy wet snow, there were some power outages, and as you can see, some of the counties actually, that red is actually 50 to 75% of customers without power. So that's pretty impactful, again, from a power outage standpoint. And this was a tweet that we sent out that day. This is a water vapor satellite loop, and the kind of green shading that you see, that's moisture in the atmosphere. And when you see that kind of approaching southern New England, that's what we like to call a fire hose of moisture. And that basically is it's almost like a hose of lots of water that is pointed at our atmosphere. So that really gave a lot of, I guess, juice for the atmosphere to produce precipitation. And not surprisingly, much of the region saw heavy rain with widespread amounts of 1 to 2 inches. And this is, a look at Chester, Massachusetts. That's around 600 feet elevation. And that is around 1:30 a.m. And you can see, it's pretty large snowflakes, but at 33 degrees Fahrenheit, the snow was struggling to accumulate. And now going up to just over 1,000 feet in Cummington, Massachusetts, they received 9.5 inches. So you can see just, going from 600 feet to 1,000 feet, that's a world of difference. And thank this snowfall observer who gave us the snowfall measurement. And this is actually just across the border into Vermont, which is just outside of our forecast area. And he sent us this image from Twitter, and he lived just over 2,000 feet, and you can see he received almost a foot of snow. So again, the higher you go, the more snow you get from this system. And he actually did measure the liquid equivalent, just over 1.5 inches. And if you take the snow to liquid ratio, that is 7:1. So very heavy wet snow, because the typical snow to liquid ratio is 10:1. And that is the person who sent in the picture from Twitter. And he actually took a drive around the area, and and he went down to North Adams, which is at 650 feet elevation. You can see totally different picture. He received almost a foot of snow at 2,000 feet, but barely a couple of inches in North Adams. So this really posed a challenge to our forecasters, especially when the temperatures were marginal and you are not high enough for you to get mostly snow. You have to consider the different precipitation types, and one moment you may be getting snow, and then the other moment you may be getting sleet mixed with rain, and it's really hard to pinpoint exactly how the precipitation type is going to unfold. And just to give an example, in North Adams, they started with light snow, and there was even thunder snow at night at 1:30 a.m. And then it changed over to light rain as the temperature warmed to 36 degrees. And then it flipped back to light snow at 34 degrees, and then it finally changed to heavy rain at 35 degrees. So very tricky forecast. And not far away from Pittsfield, Massachusetts, it started with light snow and again a little bit of thunder snow, and it actually stopped precipitating for an hour, and then it changed to light rain, and then eventually snow, and then rain. So a lot of back and forth. And this was a mesoscale discussion put out by the Storm Prediction Center, and actually highlighting the area that where they think periods of heavy snow are most likely. And you can see the hatch area actually it included northwest Massachusetts in the high terrain, and it stretched out into the Green Mountains in Vermont and the high terrain in upstate New York. And let's take a look at the winter weather ingredients. And very generally speaking, there are three ingredients that you want to look for or examine when you want to determine what kind of winter weather you can get. So they are cold air, lift, and moisture. And so firstly, cold air. Without cold air, you're not going to get snow or ice. And because it's just not cold enough. But although sometimes you can get heavy snow when it is precipitating hard enough, because that leads to the cooling of the atmosphere, and sometimes you may start off as rain but then change your flip over to heavy snow, and it has to be snowing heavily to overcome the warm ground temperatures in order to accumulate. Because otherwise you're just going to get light snow, or you might be switched over to a light drizzle if it is not heavy enough. Secondly, lift. Basically, that's the upward rising motion of air that is needed to form clouds and precipitation. Without lift, you don't get precipitation, period. And lift can be produced from different sources. One of the most common is a frontal passage, either a warm front or a cold front, and orographic lift. And we're going to talk a little bit about the impact of the high terrain in the Berkshires later. And thirdly is the moisture. You can be very cold, but if the air is dry, you're not going to squeeze out snowflakes. So air flowing over a large body of water, such as the Great Lakes or the ocean, are an excellent source of moisture. And and taking a look at the NAM, this is at 925 millibar. That's around 2,500 feet, which is roughly the elevation of the higher terrain in the Berkshires. And notice how focus on the circle in the center of the figure, and you can see the wind bobs. And so if you look to the right of the circle, you see the wind bobs with flags. That's a flag actually is 50 knots, and each line that represents 10 knots. So the wind bumps to the left of the circle represent lower wind speeds, and the ones on the right represent higher wind speeds. So if they're all traveling in the same direction, you would expect what we call speed convergence from the right to the left. So when you get speed convergence, you generate lift and upward rising motion of air, and that in turn leads to clouds and possibly precipitation. And then the next question is the temperature going to be cold enough? So at 925 millibars, again, around 2,500 feet, it's around -2 Celsius, which is 28 degrees Fahrenheit. This would not be cold enough for the coastal plains, but in this situation, it was cold enough for the high terrain because they are at 2,500 feet. And taking a look at the 850 millibar frontal genesis, this is a little bit higher at 5,000 feet. And frontal genesis is defined as the lift produced by a contrast in temperature. So generally, the stronger the frontal genesis, the more upward rising motion of air, and again, that creates more precipitation. And focus on the bright colors in the figure. So the bright colors represent greater values of frontal genesis, and again, more lift and more potential for clouds and precipitation. And this is a more zoomed in look at vertical velocity at 5,000 feet. And again, I want you to focus on the bright colors that again represent areas of higher values of vertical velocity. And vertical velocity is the speed at which the air is rising. So higher the velocity, the faster the air is rising, and again that leads to more clouds and precipitation. And going up further to 10,000 feet, and here you can see, notice that swath of red focus on the Berkshires, and actually, and then zooming out, you see that swath of yellow across pretty much the whole of southern New England. Basically, what this is saying is that there's very strong southerly winds at that elevation, which helps transport the moisture of the Atlantic Ocean, and sometimes you can trace the source of moisture all the way to near the equator. So again, stronger wind, more moisture transport means more precipitation. And let's summarize the three factors that go into the winter weather ingredients. So do we have cold air? Yes, for the high terrain. Not so much for the coastal plains, because the high terrain is high enough. It taps into the sub-freezing temperature at 2,500 feet. So yes, there's cold air for people living in the burbs. Secondly, there's lift as well, produced as a result of the high terrain and frontal genesis. And last but not least, there's moisture at 10,000 feet because of the strong southerly flow of the Atlantic Ocean. So at this point, I'm going to pass it back to Joe, who's going to talk about high resolution guidance.
Okay, thanks, Rodney. So we use high resolution guidance a lot when we get closer to the actual storm itself. So typically, less than 48 hours is the window. So that helps us determine more of the details of storms, things like the rain-snow line and bands of heavy snow. If it's, in most situations with a storm, we can have a pretty good idea in that time frame. But some situations, these can't be resolved until almost less than 24 hours before. Sometimes even not until the storm is happening and we're watching more radar and satellite and weather observations to determine those things, but they're really useful once we get to about 48 hours of a particular event. So we're going to run through some of that here. And if you've seen our webinars before, you're familiar with the HREF. That's the High Resolution Ensemble Forecast, which is kind of a conglomeration or a bunch of individual high resolution models, and it helps us iron out kind of the uncertainty. So this is a look at the 48-hour forecast. This is really at the beginning of that window I was talking about. 24-hour mean snowfall. So what you can see is definitely the higher terrain is being focused on here. And you can even see a little bit in the hills of northern Worcester County up into New Hampshire. But most notably, the Berkshires stand out pretty well here with a mean of about 4 to 6 inches and even more as you head up into Vermont. So again, that's kind of just a straight average. So you've got some models within that ensemble that are higher, some that are lower, and some that are close to that. But at least what it does is, not necessarily focusing on the values, it's focusing on the location. So this is telling us that, yeah, this is going to be a high elevation event with really no snowfall as you get to lower areas, Connecticut Valley and out toward the coast. Now, one of the things that the HRF has is also a maximum snowfall out of all the ensemble members. So this is kind of the worst case scenario. And at this time range, again, this is a 48-hour forecast. So we're right at the start of that window where we're going to look at this. You can see the values are much higher than the mean. If I flip back and forth, you can see pretty easily there's a big difference. So now in the Berkshires, we're into the green here, green shading, which is upwards of 8-10 inches, even some pockets of 10 to 12. Into Vermont, it's over a foot with some pockets. So actually, not too bad for a max forecast for this area. This obviously was a little bit more overdone, but showed at least the potential for that if kind of everything came together right. It doesn't mean everywhere is going to see these values, but one area within this region could certainly see that. Then as we got a little bit closer, this is now into 36 hours. And this is a look at the probability match mean snowfall, which isn't more of a straight average. It kind of holds on to those high outliers and the lower outliers. So it kind of preserves some of those extremes. But this is really not a bad forecast either. Again, it's focused on the Berkshires, lesser amounts in Worcester County, but widespread, 6 to 10 inch amounts, I think are pretty reasonable there, and over a foot as you head over the border into Vermont, which is pretty much what happened. So again, not necessarily focusing on the specific values, but looking at the location. So it's telling us pretty strong indications this is going to be a high elevation event. And one of the other things we have are various probabilities of total snowfall or even hourly snowfall. And this is the probability of receiving more than 4 inches in 24 hours, which really lights up the Berkshires and into southern Vermont, a little bit less so in Worcester County. So again, this kind of lends to high confidence that Berkshire County is going to see at least 4 inches of snow, if not more. And this is the probability just going a little bit higher, up to 8 inches. You can see still some low probabilities there in the Berkshires and even in northwest Franklin County, with higher probabilities as you head over the border into Vermont. So one other thing that we look at, you may be familiar with, are called model soundings. These are kind of looking up into the atmosphere in kind of a 3D view. So just to explain this for those who aren't familiar, the red line is a temperature curve, and this is going up in the atmosphere. So the height is going up on the left. Temperatures are going warmer on the right, but these are in Celsius. So 0 Celsius is in the middle, with below freezing Celsius on the left and above freezing on the right. So red is temperature, green is the dew point. So when these two are close together, the air mass is saturated, and when these are further apart, the air mass is dry. So this helps us identify a few things, but in this particular sounding, what I want you to key on is on the left. This is showing the forecast lift, so what Rodney was talking about from that frontogenesis primarily. But the vertical velocity is located here. So you can see where the maximum is as it extends out to the right. It's a little weaker to above and below. Where this is centered corresponds with a certain temperature on this temperature curve. So you can see between these two yellow bars, we're roughly between about minus 12 Celsius and minus 18 Celsius. Now, why is that important? That's called the maximum dendritic snow growth zone. This is where you maximize the production of snowflake. These are those big silver dollar size snowflakes that really can accumulate. So when your maximum lift is centered within this range here, the DGZ we call it, that's when you get potentially big snowfall. So if the lift is centered above that layer where it's colder, you will get smaller snowflakes that really won't accumulate as much. And same thing if it's in the relatively warmer air below. If it's centered down here, you won't get the maximum snowflake production. So this is what you really want, that minus 12 to minus 18 Celsius area. So also, if you notice on the wind, these are wind barbs as Rodney had shown on the maps before, but just plotted as you go up in the atmosphere. Notice here, once you get above, a little bit above where you've got some northerly wind, you've got a lot of southeast flow aloft, like Rodney showed at that 10,000 foot level, 700 millibars. And that also provided some added lift from what's called orographic enhancement. So as this wind runs up into the Berkshires, it's forced upward. So there's another source of lift that we have. And that led to, snowfall rates of over 1 inch per hour. So now we'll go into an analysis of the storm, kind of see how things panned out. And first of all, just to show the Berkshires for those who may not be familiar with the area, you have the Connecticut River Valley down here in the darker blue, the Hudson Valley over here in eastern New York, and in between these are the Berkshires. The elevation rises rapidly as you head out from Hampton and Hampshire counties into Berkshire County, and this is kind of the spine here of the Berkshires. North Adams and Pittsfield are located just to the west and a little bit of a lower elevation. So imagine if you're seeing the wind come across from the east. It's starting off, it's hitting this part of the Berkshires, it's forced upward, and this is kind of the maximum area where it's forced upward, and then the elevation starts to drop off a bit, so the air comes back down. Now, as the air rises, it's providing lift and helping the moisture kind of wring out, but on this side, as the wind kind of lowers in altitude, it's drying out. It's called subsidence. So that's why you'll see in our analysis there's a little bit of a shadow here from the snowfall amounts with the heavier ones along kind of right on the spine of the Berkshires. So I hope that makes sense. But here's kind of an example of what I'm talking about. At this point, this was 5 a.m. on Saturday, and heavy precipitation's ongoing across the region with heavy snow for the most part. And this is that upslope. You can see the wind barbs point to where the wind is coming from. So here it's out of the east, the northeast, and east here as well. I'm not sure, that might be an error. That's showing a southwest wind. But for what it's worth, you have this upslope flow coming from the east, and that caused air to rise. The temperatures were also a bit colder, 33, 31, and 30. Then when the air starts to sink a little bit, even a little bit, as I said, it dries out and it also warms a little bit. So now you're taking air that's 30, 31, 32 degrees and compressing it. So now it's warming to 34 and 35 on the other side, again, of the spine of the Berkshires here. So as a result, we had less snowfall on the western side of the Berkshires as we did along the east slopes from this event. So just taking a look at some of our analysis graphics, this is kind of showing a little bit to support what Rodney showed in the model forecast, but this is more of an analysis. So we talked about frontogenesis being the lift that's associated with temperature contrast, and you can see here, this was that morning at about 7 a.m. You have a lot of frontogenesis along Connecticut into southern New England. This is where it was raining hard, but also another little maximum here over the Berkshires that was producing that heavy snow with the southeast flow. Again, the frontogenesis combined with that southeast flow was producing enough lift to really wring out the moisture. Another thing we can look at are called lapse rates, and the lapse rate is a change of temperature with height. So when you have a steeper lapse rate, say where you have these orange colors, that's more favorable for heavy precipitation. There's more instability. So these are fairly steep to see, and this provided added instability. That's why we had a couple of reports of thunder, actually, because of that instability that was there. But this also helps enhance snowfall rates, and you'll often see, things like 1 to 2 inch per hour snowfall rates when you've got this kind of instability. Now, the other thing was speed convergence. This is looking down at about 2,500 feet. But it's hard to see the wind arrows in this, but you've got very strong southeast winds coming up and easterly winds running up into much weaker easterly winds. So again, as Rodney mentioned, it's that speed convergence, but instead of running into a wall, it has to be forced upward. So this is where you're enhancing, again, that vertical motion. And also you'll notice the temperature. So you've got above freezing air marginally here over the Berkshires in the red, and below freezing air in the blue. So we have this tight packing of the contours. That's a big temperature contrast over a short distance. And that's where you're getting the added contribution from the frontogenesis, which leads to more lift. So kind of all on a local scale, not a widespread feature, but something that really just occurred right near the Berkshires because of that increase in elevation. So next I've got a radar loop just to go through. This is from 11 p.m. on the 15th to 9 a.m. on the 16th. So reflectivity is on the left. This is typically just the intensity of the rain or the snow. And on the right is what we call correlation coefficient. It's a dual polarization product. I think if you're familiar with radar or have seen our webinars before, you've seen this. But the one thing I wanted to show is you can see starting at 11 o'clock to midnight as the loop gets underway, you'll see we've got some patches of heavier precip coming up. What looks like a big slug of heavy rain, maybe even some reds in there, so some really heavy stuff. But if you look at the correlation coefficient, it tells you what's happening. So we've got the darker shades of purple here. This is where you have uniform drops. So either it's all rain or all snow. And in the middle, you'll see an orange band or a lower value here. This is where you have mix. So you've got snowflakes mixed with raindrops. And you can actually see toward the end, it's forming a bit of a ring around the radar. And what that's showing is, as we get to the end here, you'll see this is all rain around the radar site. Where the beam is rising in elevation, it's about 5,000 feet up over Worcester County. It's running into that mixed precipitation. And then beyond that, it's cold enough to be detecting all snow. So what you're seeing is rain to a mix to all snow. And I'll let that go one more time so you can see it again. But that helps us determine precipitation type. So it's rain, mix, and over to all snow in the Berkshires. So as far as messaging, what did the forecast look like? This was on the 15th from the early morning forecast. And you can see we didn't have much in there. Generally, an inch or two, maybe 3 inches in spots. But again, focused on the Berkshires, focused on the higher terrain of Worcester County and even into northern Connecticut, showing, some expectation of higher elevation snowfall. And typically with these events, there's a lot of uncertainty, as you can probably imagine. So we tend to start off on the conservative side. We're not going to throw out big numbers fast, but usually they'll ramp up as we get closer to the event. And you can see this was actually the final forecast here on the left compared with what actually fell. The amounts did increase, not enough. Maximum was about 4 to 6 here along the spine of the Berks. Lesser amounts back to Worcester County. You can see we got the shape right, but the amounts certainly were a bit underdone. They actually were adjusted upward early in the morning when we started to receive reports that some places were already exceeding 5 and 6 inches of snow. So just some concluding thoughts here on the event. Again, given the wind speed, we talked about the wind convergence and marginal temperatures. This was primarily a high elevation snow event, and probably no surprise if you've seen some of our reviews so far. Definitely the local geography and orography, which is the lifting caused by the Berkshires, resulted in a considerable spread in snow amounts across short distances. Again, the east slopes got more snow in a favorable area than the west slopes. From what we saw, we showed a little bit of the HREF, but overall it did very well in pinpointing the threat area and even the snow amount probabilities. They got even better as we drew closer to the event within 36 hours. And then, an important thing is Rodney showed some photos here at the beginning. Your spotter reports not only play an important role in helping us, with storm verification, kind of how we did, and these storm reviews, but also ground truth as the storm is unfolding. Remember, this mostly occurred overnight on a Friday night to Saturday morning. So the forecasters working the overnight shift didn't have a lot to go on. They had some of those automated observations which weren't showing too much at, say, Pittsfield and North Adams. They had the webcam there, didn't show much snow sticking at 600 feet. So we really didn't know what was happening above that. And this event really was significant once you got above 1,500 feet. So it's always important, you send us your photos and your reports over social media in particular. They are used, especially overnight when we don't have a lot to go on. And also for the, as far as the radar, you have things like beam blockage or less than ideal sampling. Keep in mind the radar from Taunton, when it gets over the Berkshires, is probably close to 7,000 feet. So it's not really sampling too low. In the Albany radar to the west, there's some blockage, but also is up a good 5,000 to 6,000 feet. So really radar doesn't tell all the story, and it's these ground truth reports that you provide that really help us out. So right now what we're going to do is we're going to pause and take some questions before we get on to the next section, which is our winter weather briefing. So Rodney's going to join me again, and I'll hand off some questions to him. So question from John. What feeds the fire hose? Is it convection to the southeast of the low? Rodney, I'll let you answer that one.
Yeah, thank you, Joe, and thanks for the question. Yeah, I would say that's actually part of the equation. You need a low pressure to kind of be the focal point of the system. And on the southeast flank, you get the warm air advection, bringing in the moisture-rich air. But really, you also need you also need to look at not only the synoptic scale but also the global scale, because you're talking about moisture that could potentially originate near the equator. So there needs to be some other forcing that actually would provide a kind of a nice segue into the kind of the global patterns that could help to promote such a, like some of you may have heard about teleconnection patterns like El Nino and La Nina. But we're going to get into, I believe we have a webinar about global teleconnections, and if you're interested in how the circulations around the world influence the weather patterns here in the U.S., I would encourage you to join us on that webinar. But long story short, the low pressure that you see on the surface map is only part of the equation. You really need to take a much broader view.
Right. And John, some of that fire hose that you're seeing, sometimes it originates just off the Carolinas. Sometimes it feeds deeper into maybe down toward, the Bahamas, and sometimes even, as Rodney said, almost down to the equator. So, it really depends on kind of how the jet stream is configured, whether it's going to help transport that moisture up northward or not. So, much more of that. There's a little bit of that in our Climate 101 webinar on YouTube, but as Rodney said, we'll have a lot more on that when we get to our webinar talking about the global weather patterns. So let's see. Also from John, Rodney, how is frontogenesis calculated? Looking for the units, and off the top of my head, I forget what it is. So maybe you remember.
Yeah, frontogenesis. It's since you're talking about I'm trying to. I mean, there would be a per second, I believe. Let's see. What?
Yeah, there's a rate of time involved.
Yeah, I believe it's meter per second. I have to look it up. It's something per second, but you're talking about the transfer of mass per unit time. So we'll look it up the equation again, frontogenesis equation.
Yeah, and figure it's almost like a temperature change. We're talking about temperature differences, so it's temperature differences over a certain amount of time is basically what it is. Let's see, from Kevin, how often does frontogenesis play a role in smaller scale storms such as this one? Well, Kevin, it certainly did. As we showed on that map, there was a large area across much of southern New England, but also a little secondary right over the Berkshires. So sometimes even a local temperature difference that strong. Remember, you saw the temperature there at 2,500 feet, a lot of contours. That will, plays enough of a role. So it can be on a small scale. It can also be in a bit of a larger scale. Just kind of depends on the temperature fields at that time. Question from Mike. Let's see. Mount Tom. I'm sorry. I've got to find the right question. It's from John also. So Mount Tom and Mount Holyoke in the river valleys there top out about 12 to 1,400 feet. Were these mountains not high enough to have accumulating snow? They were close, but not quite enough located in the best area with the frontogenesis, kind of where everything came together, John. So, I'm sure they did have some snow, but really it's once you got up to the Berkshires where the lift was certainly more, I would say, organized by a larger mountain range, relatively speaking. That's where everything really kind of came together. A little bit better than, Mount Tom or Mount Holyoke, which are a little bit smaller, even though they're high as well. Question from Mike, and I'll hand this one to Rodney. Did cold air damming play any role in this event?
That's a good question. So, if you talk about cold air damming, you'll be talking about, places like the Pioneer Valley, but they did not receive measurable snowfall, as far as I can remember. So in this case, it's not an ideal setup for cold air damming as well because of the orientation of the valley, the Pioneer Valley in this case, from north to south. Here you're talking about the low level flow is really from off the southeast. So you're not really to get cold air damming in our valleys. You need a northerly drainage of cold air from like in this case from Vermont. So, but it's just the direction is not ideal for to trap the low level cold air in place in places that does not have the elevation.
Okay. Let's see, a few more here. One from Chip. So he says if he understands right, there was lift from the geography, lift from the wind speed, and lift from the temperature gradient, and maybe something more. What was the relative contribution of each component in this event, and is that typical? So which was the largest? Rodney, I would probably say the largest factor was the wind speed convergence that we showed. That's usually a big factor at that 10,000 foot level. Remember, we had the really strong winds running into almost much lighter winds. So that was probably the most significant. I think second is probably the geography for sure. And then the third, maybe the temperature gradient. I don't know. What do you think, Rodney? Does that make sense?
I would absolutely agree with this order because, just, the sheer difference in wind speed, across a relatively short distance. So think about, on the highway, you have like collision between vehicles, someone driving very slowly and someone driving very quickly, and then they collide. When you think about air particles colliding, they have nowhere else to go except to rise upward. And then the secondary contribution would be the terrain or orographic lift. So in this case, the east-facing slopes in the Berkshires got the most amount of snow. Of course, above a certain elevation. And then finally, the temperature gradient, there wasn't really like a strong cold front or anything. It was just kind of, almost kind of, I believe it's slightly above normal temperatures, but that's what you need. You needed the elevation. It's almost like a early springtime event as opposed to a midwinter event.
All right. Let's see, a couple more here, and then we'll get to our briefing. From Gabriel, this is a question we always hear, Rodney. How much snow would we have had been looking at near Boston if there was cold air in place? Well, if we said, took the liquid, say it was 1.5 inches, we say 15 inches off the bat, but yeah, but not really, because you wouldn't have had all that precipitation if there was cold air in place. Remember, we had southeast winds, in the surface, so the moisture wouldn't have come in. We wouldn't have had as much moisture into eastern Mass if the wind, say, was out of the north to help us get that cold air in place. So, hard to say, but in this case, even if it was colder at the ground level, there wouldn't have been much accumulation just because it was just marginal at best. If we had cold air aloft, Boston probably would have been like 35, 36 degrees with snow and not much sticking. So, the easy answer is to say something like 15, but really, you wouldn't have had the same factors in place to produce all of that precipitation. So always a tough question, but if you want to say 15, you can say 15. From Landon, how was the vertical velocity product generated? Landon, that's actually the final result of looking at all the different components that cause lift. So it's what Rodney and I talked about. It's kind of the final answer of taking the orographic lift up the side of the mountain, plus the frontogenesis, the lift from that, and putting and some other things and putting those all together into a final product to show kind of the total lift. So it's calculated by the model as a sum of kind of all these different contributors to lift, if that kind of makes sense. And from Donna, and then this will be our last one before we move on. What about temperature inversion, or is the elevation taking care of creating the snow? There is the temperature inversion there, but I probably didn't point this out on the sounding, but it was entirely below freezing, so there wasn't any issue with like mixing, sleet or anything like that. The sounding was entirely below freezing, so you had snowflakes as they were falling from the clouds all the way down to the ground. So it's really just it's a cold sounding, it's moist, and you have that lift right in that magic, minus 12 to minus 18 zone. So, Donna, I hope that answers your question. But if not, or anyone else thinks of anything, just shoot me an email and I can certainly get the answer to you.